I'm Norman Wallberger. Today's famous math problem goes back to the ancient Greeks and touches base with a lot of foundational aspects of modern mathematics, some of which are not often properly laid out. In particular, the crucial idea of the area of a figure. So famous math problem number 16 is how to find the area of a triangle from its three sides. And this is a solved problem, but it's a rather difficult solved problem, so it gets d equals 5. It goes back to Archimedes and Heron. Archimedes, the greatest thinker of all time, in my opinion, and Heron, a mathematician who lived quite a bit after him, around 60 AD. Heron's formula, as it's usually known, is the following: that if you have a triangle, ABC, with side lengths, little a, little b, and little c, so these are the lengths or the distances between the vertices, then the area of this triangle is given by this formula right here. It's the square root of s times s minus a times s minus b times s minus c, where s, often called the semi-perimeter, is the sum of the three side lengths divided by 2, so the average or halfway around the triangle. Alright, so this is an important formula. So this is in some sense a resolution of the problem, because if you know then the three side lengths, then you can compute, using this formula, the area of the triangle. Heron's formula is often not studied so much these days. In former times, almost all students of mathematics or geometry would have learnt, or at least been exposed to, Heron's formula at some point. These days that's not always the case. That's generally considered a negative aspect of modern education, but in my opinion the situation is a little bit more subtle. I actually think it's actually a good thing that Heron's formula itself is not taught anymore, because it is not the right formula, in my opinion. Let me try to illustrate that with an example. So examples often shed light on things. So let's have a look. Here is a grid plane, or just a bunch of parallel, equally spaced lines in the x and y directions. And here's a triangle, ABC. Okay, and let's consider the area of this triangle. Now we can calculate the area of this triangle in a relatively simple way using a formula that goes back to Euclid. And we can do that by thinking first about the rectangle in which this triangle appears. This rectangle has base 1, 2, 3, 4, 5 and height 1, 2, 3, 4. So the area of the is 20. So we can calculate the area of the triangle by taking the area of the rectangle and then by subtracting the three triangle areas that are around it. So this one here, for example, is a 4 by 2 triangle. It's a right triangle with one side here 4 and perpendicular side 2. So Euclid's well-known formula is base times height over 2. All right, so the area of this triangle here is 4 times 2 over 2. And we can see that directly because this triangle here is half of this rectangle. All right, so if you believe the formula for the area of a rectangle, then the area of this kind of right triangle is just half of that. Similarly, this triangle here has sides 3 and 3, so its area is 3 times 3 over 2. And this triangle down here is area, it's 5 times 1 over 2. This is a simple calculation that we can do with just basic primary school arithmetic, and we can get 9. And does that sound reasonable? Is the area of this triangle roughly 9? Well, here you can see a little square. So there's 1 square, 2 squares, 3, 4 that are completely contained inside the triangle. And then there's, you know, a little bit of one here, here, some pieces left over. And we can kind of imagine that, yes, roughly, those are going to add up to something pretty close to 9. So it's a reasonable. Now suppose we have a look at the same problem from the point of view of Heron's formula. So for that we require the side lengths, which are given to us by Pythagoras' theorem. So this side length here, let's call it A because it's opposite to the vertex A. Here it's the hypotenuse of a right triangle. And so this is 3, this is 3. So the Pythagoras' theorem will tell us that this length squared equals 3 squared plus 3 squared. Or in terms of distances or lengths, A equals the square root of 3 squared plus 3 squared, which we can write as 3 root 2. If we have a belief in confidence in our square roots. Similarly, this side B, 4 and 2, gives us square root of 4 squared plus 2 squared, which is 2 times root 5. And this one here, C, is square root of 5 squared plus 1 squared, square root of 26. So Heron's formula in this case would say that this area of the triangle is, first of all, there's a big square root, and inside the square root there is, well, here's this quantity S. So S is 3 root 2 plus 2 root 5 plus root 26, all divided by 2. And then the next one would be S minus A. Well, if this is S and we subtract A, then it really amounts to changing the plus sign here with a minus sign. And here's S minus B, the minus sign now there. And here's S minus C with a minus sign in front of the root 26. And so that's what we have to calculate. Now that's a rather onerous calculation because naively we would say, well, we need to get out our calculator and we have to calculate this quantity, which our calculator only does approximately, and then this quantity, which it only does approximately, and similarly this one and this one. And we have to multiply them all together. And then we have another square root to invoke. Get our calculator out. And supposedly after we do all of this, we're going to get, well, we should get 9, but do we? If you actually do it with your calculator, my guess is you're not going to get 9. You're going to get some decimal expansion which is pretty close to 9. Maybe 8.999985574, or maybe 9.0000149, something like this. So it's not entirely obvious that this is really a good formula, because in this simple example, it doesn't give us, at least immediately, the very simple natural answer that we know is actually correct. There's another reason, a more conceptual reason, why this formula is fraught with difficulty. And that's to do with the square roots. So in my opinion, the true solution to this very important problem was first really clearly enunciated only in 2005, relatively recently, with the publication of my book, Divine Proportions, Rational Trigonometry to Universal Geometry, published by Wild Egg. So in this book I lay out this new theory of rational trigonometry that I hope you've learnt or heard about at least. And a lot of things become much clearer and more precise and natural and general once you get a little bit of rational trigonometry under your belt. And this is a great example here. So I'm going to show you now the right formula, right, that replaces Heron's formula. So the key idea that we're going to need is the idea of quadrants, a way of measuring the separation between 2 points, which in fact really goes back more to the orientation of the ancient Greeks, to Pythagoras and to Euclid. So if we have 2 points in the plane with coordinates, say x1, y1 and x2, y2, and the points' names are capital A1 and capital A2, then we can define the quadrants between A1 and A2 to be this number. So it's x2 minus x1 squared plus y2 minus y1 squared. That will of course not be unfamiliar to most students of mathematics. And most students will recognize that the usual distance between these 2 points, or equivalently the length of the line segment, is actually naturally defined in terms of the square root of this quantity. First you calculate this, and then you take a square root, and you get the distance or the length. In rational trigonometry, we realize that this quadrant is primary. It's more fundamental than distance. And it really explains why if you go back to Euclid and you read the elements, Euclid avoids distance and length measurements. He goes out of his way to avoid them. And it's basically because he knew of the problems with the irrationality posed by this square root operation. So in order to make sense of this formula, you really need a proper theory of the square roots. As I explained in my Math Foundations series, this is highly problematic. Modern mathematics does not have a proper theory of square roots. I know this may sound heretical, but if you look at my Maths Foundation series, there's one that says something like uncomfortable truths with square root of 2. Then you will get a sense of the problematic aspect of the square root. In any case, the quadrants is algebraic, it's pleasant, it's more general because it applies to more general fields. So in rational trigonometry, the quadrants is elevated to a primary quantity. Very, very good point of view to have. So with the notion of quadrants only, we can state the two most important formulas in mathematics. The first is Pythagoras' theorem, which I hope you all recognize as being the single most fundamental theorem and formula in mathematics. It says that if you have a triangle A1, A2, A3, then the side A1, A3 and the side A2, A3 are perpendicular precisely when the following relation holds between the three quadrants of the sides. Precisely when Q3 equals Q1 plus Q2. And Pythagoras' interpretation of this, and Euclid's interpretation of this, was it's a statement really about three squares, the areas of three squares. The Q2 really represents the area of a square built on that side, as does Q1, as does Q3. So Pythagoras is really a statement about one square area plus another square area equals a third square area, precisely when we have perpendicularity between these two sides. The square root formulation that many of you will have been exposed to in your texts is an aberration. It's a distortion of the essential content of Pythagoras' theorem. Very important to understand this. Okay? It's not one distance squared plus another distance squared equals a third distance squared. No, no. It's one squared area plus another squared area equals a third squared area. Or, in other words, one quadrant plus another quadrant equals a third quadrant. Very, very fundamental understanding to have. And the 21st century is not too late to adopt this higher point of view. Especially since, as a benefit, we can get at the second most important formula in mathematics. And here I mean the ones that are actual formulas, not like laws of arithmetic that everybody kind of knows. Actual formulas that are not entirely obvious. So the triple quad formula, what is it? It's very much an analog of Pythagoras' theorem, where the perpendicularity between these two sides is replaced with a parallelism between these two sides. So that A1, A3 is parallel to A2, A3, precisely when this more complicated relation holds between the three quadrants. So it's really a statement about collinearity of points. The 3 points are collinear precisely when this relation holds. Q1 plus Q2 plus Q3 squared equals 2 times Q1 squared plus Q2 squared plus Q3 squared. And again, it's ultimately a formula about areas. It's really about the area on this side, the area on this side, and the area on the big side. Now, if you're a 20th century geometry student, you say, well, wait a minute, so that's replacing the distance 3 plus distance 1 equals distance 2. That's right. It's a quadratic replacement of that sort of pseudo-linear relation between distances or lengths. The advantage in this one, well, it has many advantages, but one of them is that it doesn't depend on the order of the 3 points. Right? So the statement that D3 plus D1 equals D2 depends on you knowing the relative position of those 3 points. If I change the position, then the relation between the 3 distances changes. This quantity is symmetrical. It's a symmetrical relation that is independent of the order of the points. Also, it doesn't involve any square roots, and in fact it works over a general field. So we can talk about geometry much more generally. Okay, so once you learn a little bit of rational trigonometry, you start to appreciate how these two formulas sort of fit together to really form the pillars of geometry. And if you'd like to have an elementary introduction to that, you can look at the Wild Trig video series. Of course, if you want a more in-depth discussion, you need to get my book and read it. Read all of it. Alright, so here is the true formula that captures the area of a triangle in terms of its 3 sides. This formula really was only clearly laid out, I think, in my book for the first time. Although in reality, many people will have discovered this at some level over the last few millennia. Okay. I'm going to attribute it to Archimedes because, first of all, Heron's formula was probably known by Archimedes. We have Arab sources that suggest that, so we don't have all of Archimedes' writings, unfortunately. And but we can guess from what other people wrote about Archimedes that he knew certain things. And I'm fairly confident that if we presented this formula to Archimedes, he would look at it for 10 minutes and say, yes, of course, that's correct. Okay, so what is Archimedes' formula? Well, it's that the area, say delta, of a triangle whose quadrances are Q1, Q2, and Q3 is given by the following relation. 16 times the area squared equals Q1 plus Q2 plus Q3 squared minus 2 times Q1 squared plus Q2 squared plus Q3 squared. So this is just the difference between the left-hand side and the right-hand side of the triple quad formula. The triple quad formula is telling us that if this quantity happens to be 0, then the 3 points are collinear. What we're seeing now is that this expression actually extends not just to collinear points on a line, but it extends to an understanding of the area of a triangle in the plane. It's exactly the difference here that is measuring the area, or actually more precisely the area squared, with a factor of 16 out front. And I also rewrite this formula in this way. This is an important alternate way of writing it. So the equality between this and this is an identity, which I'm going to leave to you as an exercise to check. So this is purely a formal algebraic identity. If you expand this out, and if you expand this out and compare, you'll see that they're exactly the same. So here we have 4q1 q2 minus q1 plus q2 minus q3 all squared. And I'm going to give this thing a name. So this quantity, the difference between the left and right hand sides of the triple quad formula, we're going to call that A for Archimedes. And we're going to think of it as a function, if you like, of q1, q2, and q3. And we're going to call it the quadria of the original triangle. It's not exactly the area, it's sort of the area squared up to this factor of 16. Okay, it's probably the single most important number associated to a triangle. It's a measure of how non-collinear, in some sense, the triangle is, and also how big it is. Archimedes' formula. All right, so let's look at an example. Let's go back to that triangle that we considered at the beginning. Let's call it A1, A2, A3 now, so that the notation is similar to what we have in our formula, with quadrants as Q1, and we'll denote that quadrants with a little rectangle along the side. And here's Q2, and here's Q3. And we're interested in the area of that triangle, A1, A2, A3. All right, so the quadrants now are, by Pythagoras' theorem, Q1 is, well, you look at the same right triangle, 3 here, 3 here, so 3 squared plus 3 squared, it'll be 18, so that's the quadrants there. Q2, here's 4 and 2, so it's 4 squared plus 2 squared is quadrants of 20. And quadrants here of 26. The quadria then is given by either one of these two expressions. Okay, we can use either one of them to calculate. I'm going to use this one to calculate, which is often a little bit simpler because it's a little bit shorter and because there's often a little bit of cancellation in here. Alright, so Q1 times Q2, 18 times 20 times 4. And then we have to take the difference between these two added together and the Q3. 18 plus 20 minus 26 and square it. So we get 1,440 for this product and minus, well, what is this? This is 38 minus 26, so that's 12, and 12 squared is 144 for a total of 1,296. And according to our formula, that's 16 times the area squared. Well, it turns out that this is 16 times 9 squared, and so the area of the triangle is 9. And we not had to take any square roots. We didn't have to take any square roots in calculating the sides, so we didn't have to descend to the level of approximations of infinite processes. We did not have a complicated formula to work out. It was a lot simpler than Heron's formula. And at the end, we get a nice natural number, but we're staying within natural number arithmetic. I'm going to show you, just for reference, another example. Here we have 3 collinear points. This illustrates the triple quad formula, or the case of Archimedes' formula when the quadria is 0. So we have points B1, B2, and B3, and the quadrances between them are, so the quadrants between B2 and B3, well, there's a 4 here and 2 here, so that's 4 squared plus 2 squared equals 20. You can check that the quadrants between B1 and B3 is 45, and the quadrants between B1 and B2 is 5. So these 3 numbers represent the areas of squares that you could build on top of these 3 sides. Okay, and the quadria in this case, using the original formula, sum of the 3 quadrants is all squared minus 2 times the sum of the squares of the 3 quadrants. And you can work that out. You get the difference of 4,900 with itself, and you get 0. So in this case, the quadria is 0. That's telling us that these 3 points are collinear, or that the area of the triangle that they formed is 0. This is rational trigonometry at work in a very simple but important case. Now we would, of course, like to have a proof of Archimedes' formula. So how are we going to prove this result? Well, here's a proof. And I'm going to use just a little bit of linear algebra, because most students of mathematics these days are more familiar with some elementary linear algebra than they are with elementary geometry. If you look in my Wild Trig series or my book, you can find some other proofs that are sort of more geometrical. This proof is going to rely on just some basic facts about vectors. And of course, what we have to start with is, what do we mean by the area of a triangle in the first place? This is not self-evidently obvious. We need a definition of area. And for those of you interested in that question, which is a very interesting one, please have a look at the Math Foundations 33 video, which talks about how we should think about area. So we're going to take a linear algebra point of view, or a vector point of view. And if we have 2 vectors in the plane, say u, the vector AB, and v, the vector CD, then those 2 vectors form a parallelogram, first of all. Okay, so if we just translate that one up to here and translate that one over here, we get a parallelogram, ABCD. And we can define the area of that parallelogram. We can make a definition to say that it's the determinant of the matrix we get by putting the 2 vectors in a matrix. So A, B, C, D, the determinant of that matrix. Now, if you don't know what a determinant is, well, you can have a look at my Wild Lin Alg series on linear algebra. Okay, but most of you will know that the determinant is AD minus BC. That quadratic quantity is a good measure of how big that parallelogram is. Of course, if we want the area of the triangle, we should then, by symmetry, divide this determinant by 2. Okay, so now we want to recall an important identity that goes back to Fibonacci. In fact, perhaps at some level it goes back to Diophantus, 300 AD. And this is just an identity between the numbers A, B, C, and D. It says that AD minus BC squared plus AC plus BD all squared equals A squared plus B squared times C squared plus D squared. In other words, if you expand both sides, you'll see that they're the same. Alright, so now let's prove Archimedes' formula. We're going to look at 16 times the area of this triangle squared. Alright, so this quantity here, AD minus BC squared, is almost the area of the triangle squared, but it's actually half of this all squared. So if I multiply the area squared by 16, I'm really multiplying AD minus BC squared by 4. Okay, so 16 times delta squared is equal to 4 times AD minus BC squared. And I'm going to write that by just bringing all the other stuff to the other side in this identity. So if I bring this to the other side, I'm going to have this thing squared times 4 equals 4 times this quantity minus 4 times AC plus BD all squared. So this is an immediate consequence of our definition of area with Fibonacci's identity. And now let's have a look at it. This A squared plus B squared is just the quadrants of the vector u. Now in linear algebra, the quadrants of a vector is expressed naturally and beautifully as a dot product of a vector with itself. So the quadrants of any vector v can be defined to be v dot v. So this is quadrants of u, because if you take the dot product of this vector with itself, it's a times a plus b times b. And this quantity in here is just the dot product between the vector u and v. Dot product between these two vectors is AC plus BD. It's exactly what's appearing here. And this 4, well, we can bring it inside the square, and so it would be 2u dot v all squared. Okay, it's getting pretty close to Archimedes' formula, and all we need to do now is observe that we can write what's inside here, this 2u dot v, in terms of the quadrants of the three vectors u, v, and w, which is the vector going from b to c here. So the vector w is the difference between the vector v and the vector u. It's v minus u. So why is this equal to this? Well, it's because of this very important identity in linear algebra, sometimes called polarization identity. Okay, which says that if you have two vectors u and v, then the following is true. If you take u dot u plus v dot v minus v minus u dot v minus u, then what you're going to get is 2 times u dot v. Okay, and why is it? Well, it's because this dot product is linear in both of its entries. So when you take the dot product between v minus u and v minus u, you're getting v dot v with a plus sign, you're getting u dot u with a plus sign, and you're getting v dot u and u dot v both with a minus sign. And since the dot product is symmetric, the v dot u is equal to u dot v, those two terms together with a minus sign in front of them combine to give 2u dot v. And the other two terms canceled with these ones here. Alright, so that's why we can replace the 2u dot v that's occurring here with the quadrants of u plus the quadrants of v minus the quadrants of w, because this is the vector w. There's w dot w. And that's all there is to it. So 16 times delta squared equals 4 times quadrants of u times quadrants of v minus this combination, quadrants of u plus quadrants of v minus quadrants of u squared. And we saw that that was an alternate form for Archimedes' formula. So if you teach linear algebra and you teach inner products or dot products, of course you should expose students to this. Right? This is the most important application of dot products. It is. To the area of a triangle. It's absolutely fundamental. Right? This calculation or something in that direction is something that all undergraduates really must learn and see. Very, very important and crucial. But of course you have to have made this mind switch a little bit, that you're going to talk about rational trigonometry instead of that 20th century stuff with distances and angles. Okay. It's all algebraic. So a reward for having followed that algebraic derivation of Archimedes' formula is that we can very easily now move to a relativistic application. We can change our orientation from Euclidean geometry to the relativistic geometry that's important in physics to understand Einstein's special and general theories of relativity. And we don't have to do very much here. It's just very minor variants on what we've just done. All right, so just in one slide, let me give you some sort of new directions of thinking about it. Very important if you're a physics student. All right, first of all, we're going to define a new dot product. Okay, we're still working with vectors in the plane, and we have vector AB and another vector CD. Let's define a new dot product, denoted with a little bit of a circle there. Okay, to be AC minus BD. Just like the usual Euclidean one, except there's a minus sign there instead of a plus sign. And correspondingly, we'll define the quadrants of a vector now as still v dot v, but now it's v circle dot v. So for example, if v happens to be CD, then the quadrants of v will be c squared minus d squared. This is the kind of thing that you do in relativistic physics. In that context, you don't want to take the square root because sometimes these vectors can have positive quadrants and sometimes a negative quadrants. And if the quadrants is negative, then taking a square root is more problematic, even more problematic than it usually is. With rational trigonometry, which is the natural framework for physics, okay, you don't need to worry about that because you avoid square roots, or at least try to. All right, so here is a variant on Fibonacci's identity. Okay, it's minus AD minus BC all squared plus AC minus BD squared equals A squared minus B squared times C squared minus D squared. And you can verify that just as easily as you verified the former one. Just expand both sides and collect terms and see that they're both equal. Alternatively, if you're a little bit more algebraically sophisticated, you can think about replacing B and D in the previous formula with I times B and I times D in a formal sense. Okay. All right. Well, then really the same derivation that we had before, but now applied to this formula. Here's AD minus BC. That's still the determinant of the two vectors. So if we look at minus 16 delta squared here, we're talking about this quantity times 4. And so we can write that as 4 times this minus 4 times this. And this is the quadrants of the vector u in this relativistic sense. Here's the quadrants of the vector v in this relativistic sense. And here is minus 2u dot v, where this dot is this circle dot, the relativistic inner product. And just as before, we can rewrite this thing here because it's only properties of the bilinear form. We can write it like this, and we see that we get exactly the same expression for the quadria as we did in the previous case. Exactly the same, except now the interpretation is that these are all relativistic quadrances. And crucially, that we're not getting 16 times the area squared, we're getting minus 16 times the area squared. So we can still get at the area of the triangle, It's the same area, but the metrical structure can vary. So it's a relativistic Archimedes type formula. So we see that this rational trigonometry approach not only allows us to get nicer formulas more simply, but it allows us to extend our formulas beyond the usual framework, so that Euclidean and relativistic geometries really come together and really are part of the same story. They're ruled by the same laws of rational trigonometry. I think the physics community could benefit a lot by thinking about the consequences of that. And more generally, I might add, if you're a physics student aspiring to be a great physicist, one thing you might think about is how to eliminate square roots. Okay? The presence of a square root in a theory is always some kind of indication that you haven't quite understood things the best way. Right? So this is a surefire way of increasing your understanding by reformulating theories that currently have square roots so that they don't have square roots. You learn something invariably, you learn some deep facts about the situation by thinking about things that way. So it's a good piece of advice for you. All right, in our next famous math problem, we're going to go to the 20th century, and we're going to look at a famous problem that was really enunciated by Gödel, prominent logician of the 20th century. That's really cast a large shadow over a large part of modern mathematics. It's this question of whether all true facts in mathematics can be proven. Very interesting problem. So we'll have some interesting, hopefully, things to say about that in our next video. I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.